Minus 38 degrees, that is not a temperature, that is a warning, and Volkov knew it. He had watched 3 men on his pipeline crew lose fingers to that kind of cold. He had seen truck engines crack in half overnight. He had watched a poorly built cabin. A nice-looking cabin, actually, with a metal roof and new windows, collapse under a single night of wet snow because the builder trusted a shape that Alaska had no respect for. Volkov was not going to make that mistake. Collapse under a single night of wet snow because the builder trusted a shape that Alaska had no respect for. He was standing on 6 acres of raw spruce forest in the Matanuska Valley, boots sinking into 6 inches of early October snow, thermos of black coffee steaming in his hand, and he was looking at a piece of flat, south-facing ground like a man solving an equation. 11 years of pipeline money had bought him this land. Not a structure on it, not a road through it, just trees, frost, and possibility. And somewhere in his chest, past the cold and the silence, he had already decided what was going up on this ground. Not a log cabin, not a timber frame, not a conventional stick-built box with a peaked roof that would argue with every blizzard for the next 50 years. An arch. A long, low, corrugated steel arch that would shed snow the way a dog sheds water, shrug off wind loads that would rip the walls off conventional structure, and sit on this Alaskan ground for generations without complaint. A Quonset cabin, but not the kind you are thinking of. What Volkov was about to build was something the survival handbooks don't teach and home improvement channels don't cover. A structure that looks almost too simple from the outside and performs almost beyond belief on the inside. And by the time the story is finished, you are going to understand exactly why the smartest builders in Alaska keep coming back to this shape, and exactly how Volkov executed from bare ground to finish home for a number that will genuinely surprise you. Stay with this. Most people who see a Quonset hut for the first time think it looks industrial, maybe military. They think of surplus structures rusting at the edge of old airfields, drafty and cold and purely functional. They are not wrong about the history. The original Quonset design was developed in 1941 at Quonset Point Naval Air Station in Rhode Island. The military needed a shelter that could be shipped in pieces, assembled by a small crew with basic tools, and standing in hours. They built over 150,000 of them during the Second World War. After the war ended, surplus units were sold for almost nothing and ended up everywhere. Farms, backyards, the edges of mining operations across the American North. Alaska received more than its share. But here is what people miss when they dismiss the shape as industrial or old-fashioned. They miss the engineering underneath it. The arch is one of the most load-efficient shapes in structural history. There are no vertical walls to catch a wind-low broadside. There is no flat roof to accumulate the kind of wet, heavy snowpack that collapses conventional structures in serious winters. There are no sharp corners where ice can work its way into a seam over years and pry the building apart from the inside. Instead, every load the arch receives, wind pressure, snow weight, thermal expansion, seismic movement, gets distributed evenly around the entire curve and transferred smoothly into the foundation. The arch does not fight the load. It redirects it. That is not a building strategy. That is physics. Volkov knew the history. He also knew the physics. And he had spent 18 months on his land before he broke a single piece of ground, watching where water moved in April melt, tracking which corners of November wind hit hardest, learning where the 4 hours of low December sun actually landed. 18 months of watching. Most builders would have broken ground in the first spring. Volkov waited because he understood that in Alaska, a building that does not match the land it sits on is not a building. It is a slow disaster. When he finally ordered his kit, he chose a supplier in the Pacific Northwest with over 20 years of Alaskan clients behind them. The dimensions: 32 feet wide, 48 feet long, peak height 16 feet at the crown of the arch. That gave him 1,536 square feet of interior floor space, enough for a full-time residence with a dedicated workshop at the rear. The panels arrived on a flatbed truck in late August, stacked, banded, laser-cut, pre-drilled. Assembly required a ratchet, a rubber mallet, and 2 willing hands. But before a single panel touched the ground, Volkov did the work that most people never see and never credit and never understand until it is too late. He built his foundation. In Alaska, the foundation is not the base of the building. It is the argument for why the building will still be standing in 20 years. Most people pouring money into a build in the lower 48 think about foundations as a formality: dig, pour, wait, build. In permafrost-adjacent ground, that thinking will cost you everything. Volkov did not pour a concrete slab. A slab in his ground required a heated enclosure to cure properly and created a rigid, thermally conductive surface that would work against him in every freeze-thaw cycle for the life of the structure. Instead, he excavated 18 inches across the entire footprint, filled the excavation with compacted crushed gravel, laid a continuous moisture barrier across the surface, and finished with a final compacted gravel layer on top. What does a gravel pad foundation do that concrete does not? 3 things simultaneously. It drains freely, so water that finds the edge of the structure has nowhere to pool and no opportunity to freeze against the foundation wall and lever it apart. It acts as a thermal break between frozen ground and the building floor system, slowing the path of ground cold upward into the living space. And it allows the building to shift fractionally with seasonal frost heave without cracking or fracturing the way a rigid slab does. The ground moves in Alaska every year. A smart foundation moves with it. Around the perimeter of the pad, Volkov poured short concrete grade beam sections anchored with J-bolts to receive the building's base channel. The outside face of each grade beam section received 2 inches of closed-cell XPS foam board, extending 18 inches below grade, interrupting the thermal pathway that cold ground would otherwise take straight to the foundation edge. He finished this work in 3 weeks, mostly alone. When it was done, it looked like almost nothing, a flat gravel rectangle in the spruce forest with a few bolts sticking up from the perimeter. Volkov knew it was the most important thing he would build on the entire 6 acres. The arch panels went up in 9 days. 2 neighbors helped, men Volkov had known from his pipeline years, working in exchange for his labor on their properties the following spring. The system was exactly as the engineering documents described. Each corrugated panel was shaped to a precise arc. When the sections bolted together their overlapping ribs, the cumulative curve of the arch emerged naturally without any external forming, any temporary framework, any specialized equipment. They started at the base channels on both sides and worked upward and inward simultaneously. 2 crews closing toward the crown, meeting at the ridge cap that sealed the apex. By the 4th day, the basic show was standing. Volkov walked inside alone, that evening with a headlamp. He stood in the center of the empty steel tunnel and listened to the wind pick up outside. The arch hummed, not a creak, not a rattle, not the groan of a structure fighting its load, a low, single-frequency vibration, like a bridge deck under a loaded truck, the sound of form doing precisely what it was designed to do. He stood there for a long time. Now here is where most Quonset builds go wrong. And this is the part that nobody talks about clearly. The steel arch provides 4 walls and a roof in a single curved surface. What it does not provide is end walls. The builder must close both ends, and the decision about how to do that determines the building's character, its thermal performance, and its long-term livability more than almost any other single choice in the entire build. Volkov had studied other people's mistakes. He had seen end walls framed in dimensional lumber and sheathed in plywood, standard stick construction, which functions adequately in moderate climates and fails predictably in severe cold through thermal bridging, vapor infiltration, and the steady accumulation of moisture in wall cavities that never fully dry in Alaskan winters. He had seen end walls built from stacked cordwood, which is beautiful, which has excellent thermal mass, and which requires a level of skill and available time that he was not going to pretend he had in the first building season. He chose a hybrid that solved both problems. The end walls were framed with doubled 2x8 lumber, creating a wall cavity of 7.5 inches deep. Into this cavity, closed-cell spray polyurethane foam was applied from the interior side, filling every corner. Every irregular transition between the flat end wall framing and the curved edge of the arch panels where no bad insulation could ever conform completely. The exterior face of each end wall was clad in rough-sawn local spruce boards in a board and batten pattern, stained dark, applied in a configuration that shed water cleanly downward and gave the building its now distinctive face. The corrugated steel arch rising from a handmade timber end wall, something that looked simultaneously utilitarian and deeply considered. The front end wall incorporated a salvaged double-pane window, a solid-core insulated door with compressed Scandinavian weather seal, and a covered entrance vestibule framed from log sections cut during the site clearing. The vestibule was not aesthetic. It was thermodynamic. Every time a door opens between a heated interior and a -30 exterior, a column of warm air exits, and a column of cold air enters in an exchange so fast and so complete that a single door open event in severe cold can drop interior temperature by several degrees in a small space. The vestibule breaks that exchange into two smaller events separated by an intermediate air buffer. Firewood was stacked on both sides of the entry path through the vestibule, dry undercover, and adding significant thermal mass directly flanking the building's primary cold air infiltration point. Insulation. This is where Volkov spent more research hours than on any other single aspect of the build. Because the corrugated steel arch presents an insulation challenge that flat-walled buildings simply do not share, and getting it wrong does not produce a cold building. It produces a wet building. And a wet building in Alaska is a destroyed building in slow motion. Steel conducts cold at a rate that wood does not. Without a continuous thermal break between the exterior steel surface and the interior airspace, the inside face of the arch panels will drop below the dew point of the interior air on cold days and collect condensation. That condensation runs down the panels, pools at the base, soaks whatever insulation and framing it contacts, and creates the conditions for mold, rot, and structural decay behind a finished interior wall where you will never see it until the damage is severe. Volkov's solution was a secondary interior framing system built entirely away from the steel surface. He constructed a wooden framework inside the arch that stood 4 inches off the steel panels, following the curve of the arch with curved top plates cut from plywood. Into the cavity between the arch surface and this interior framing, closed-cell spray polyurethane foam was applied to a continuous depth of 3.5 inches. Closed-cell foam at that depth achieves an R value near R21 in a single layer. More importantly, it adheres fully to the steel surface, eliminates every air gap where condensation can form, and adds measurable structural rigidity to the arch panel assembly. It is the only insulation material that solves the condensation problem, the air infiltration problem, and the thermal performance problem simultaneously when applied against a metal surface. Over the spray foam layer, between the interior framing studs, he packed bats of mineral wool, not fiberglass. Mineral wool maintains near full R-value performance even when it absorbs moisture, resists fire naturally, and does not provide a growth substrate for mold. The complete wall assembly through the arch achieved approximately R38. The end walls, with deeper framing cavities filled entirely with closed-cell foam, came in near R45. The floor system, rigid foam board under a tongue-and-groove plywood subfloor, added R30 underfoot. Volkov's Quonset cabin had a thermal envelope tighter than most purpose-built passive houses in the continental United States. Heating a well-insulated arch building in Alaska is, counterintuitively, not the hard problem. The hard problem is preventing overheating. On clear winter days when the sun bounces off unbroken snow and pours through south-facing glass, and the wood stove is loaded and the building's thermal envelope is retaining everything it receives, interior temperatures in a tight Alaskan structure can climb past comfortable faster than most people expect. Volkov had planned for this with operable high vents at both end walls, positioned at ceiling level where warm air accumulated, which would be cracked open in minutes to vent excess heat without disturbing the main living space. His primary heat source was a soapstone face with stove rated for spaces up to 2,000 square feet, deliberately oversized relative to the building at full thermal performance. A larger stove running at low output burns cleaner, produces less creosote, and operates more efficiently than a correctly sized stove pushed to its rated capacity. He's centered on the floor plan equidistant from both end walls so radiant heat spread in every direction. Soapstone absorbs heat at a high rate during active burning and releases it slowly over hours after the fire dies, eliminating the temperature spike-in crash cycle that plagues wood-heated spaces. A backup propane wall heater near the front entry was sized specifically to maintain above freezing temperatures during extended absences without requiring the wood stove to run. The chimney penetration through the arch received a professionally installed double-wall insulated stainless steel flue with a purpose-built roof boot maintaining full weathertight integrity at the panel penetration point. Volkov had seen enough improvised chimney penetrations fail, leaking both water and air, in old Quonset and barn conversions that he treated this detail as non-negotiable. He spent more on the flue system than on the stove. He has never had a problem with it. Water, power, waste. In Alaska, each of these is a decision tree that most people in milder climates never have to navigate. Volkov drilled his well to 180 feet before reaching a reliable aquifer, typical for his area, not exceptional. The supply line runs into the building through a buried insulated sleeve, entering below the frost line, and rising inside a utility chase that stays above freezing year-round from the building's ambient heat. A tankless propane water heater provides on-demand hot water with zero standby loss. The pressure tank, all valving, and the water treatment system sit inside an insulated utility closet within the building's thermal envelope, never exposed to exterior temperatures. Gray water discharges to a constructed wetland filter system at the eastern edge of the property, well clear of the seasonal creek, gravity-fed to a distribution field size for single occupancy. A composting toilet eliminated the freeze risk and mechanical complexity of a conventional septic system. Among Volkov's neighbors, this choice required no explanation. Electrical service combines a grid tie-in along the road easement with a bank of lithium iron phosphate batteries charged by a 4-kilowatt solar array on a ground-based adjustable racking system south of the building. The array is not roof-mounted. Roof mounting on a corrugated arch complicates snow management and concentrates point loads on specific panel ribs in ways the arch engineering does not anticipate. The ground frame adjusts twice yearly for seasonal sun angle optimization. In a latitude where winter days offer 4 hours of low-angle sun, every degree of panel tilt matters. Volkov moved in on the 1st of December. The interior was unfinished. A functional counter, but no cabinetry. A sleeping loft accessed by a ship's ladder, but no partition walls. Concrete board on the bathroom floor, but no tile. He had heat, water, light, and a roof that had already shed 20 inches of wet October and November snow without a creak. That was enough. He spent the first winter completing the interior in the long, dark hours, working by LED strip light and with stove glow, learning the building from inside the way you can only learn a space by living in it through its first hard season. He found where small drafts whisper in from unexpected places, a conduit sleeve imperfectly foamed at insulation, a gap at the vestibule threshold that needed a door sweep replacement. He learned that on a -20 night outside, 2 medium loads of birch held the interior at 68 degrees from evening until morning. He learned that the curved interior ceiling created an acoustic quality unlike any rectangular room. Sound did not echo and bounce between parallel walls, but was absorbed and dispersed into the continuous curve overhead, a quality that made the space feel both larger and quieter than its dimension suggested. He finished the interior through spring. That summer he built a detached sauna in the spruce clearing and extended the gravel pad to create a covered south-facing outdoor work area where he could maintain equipment and do outdoor tasks without fighting weather. 2 full winters now. Volkov has kept records the way a pipeline engineer keeps records, in columns, with dates, with numbers that do not lie. 3 to 4 cords of firewood per winter, roughly half consumption his neighbors report for conventional frame structures of similar size. A propane bill covering cooking, backup heat, and on-demand hot water that runs lower than his old utility bill for a 2-bedroom apartment in Anchorage. 0 frost heave, 0 condensation, 0 ice damming, 0 structural movement of any kind. In the windstorm last February that put trees across 3 neighboring properties and peeled the metal roofing off a shop 2 miles down the road, Volkov's arch stood without a single loosened panel. He is not selling the idea. He will be direct with you about the limitations because he thinks pretending otherwise is dishonest. Curved walls make furniture placement a genuine puzzle. Conventional shelving requires custom bracket work. The building's character comes substantially from the handmade timber end walls, which were neither fast nor inexpensive to build. The spray foam insulation system requires professional application, which means scheduling a crew and paying commercial rates. This is not a cheap build, and it is not a simple one. But when you press him on the decision, when you ask whether, knowing everything he knows now, he would do it again, He does not hesitate. He puts his hand against the corrugated steel skin of the building the way you might put your hand against the side of a horse you trust completely. He says the arch is the most honest structure he has ever been inside. It does not pretend to be something it is not. It does not argue with the weather. It does not fight the load. It receives everything Alaska sends and redirects it the way the best designed things always do, not by resisting force, but by understanding it. And then the wind comes up across the valley and moves through the spruce trees and hits the side of the arch, and the building makes that sound, that low, single-frequency hum, steady and deep and completely untroubled. For Volkov, after 11 years on the pipeline and 18 months watching his land and 14 months of building, that sounds the best sound he has ever heard. It is the sound of a structure that knows exactly what it is, and it is not going anywhere.